This video is on solutions and molarity by dilution. So a solution is a homogeneous mixture of two or more substances, and homogeneous means it's going to be the same throughout, and it's made up of two different things. It's made up of a solvent and a solute, which we'll go more in depth on in a moment. And solutions, which are in water, or when the solute is dissolved in water and water is the solvent, those are called aqueous solutions. So aqueous just means dissolved in water. A solute is the part of a solution that is being dissolved. It's usually the lesser amount. So if we're looking at Kool-Aid, for example, the solute is a solid, it's our Kool-Aid powder. And then the solvent is the part of the solution that dissolves the solute. So again, with Kool-Aid, the solvent is going to be a liquid, which for Kool-Aid is water. And when you put your solute and you mix it in your solvent, you have a solution. And most of the time in chemistry, when we're looking at a solution, you want to know its concentration. And for us, the unit for concentration we're going to be dealing with most of the time is molarity. And molarity has the unit of capital M, and it is moles per liter. And let's see, some of the notation you're going to see is these square brackets. And the square brackets, that means concentration. So if we have HCl, this is going to be hydrochloric acid concentration. A lot of the times you're probably a lot more familiar with the capital M for molarity, but in IB they're going to be using moles per decimeter cubed, and 1 decimeter cubed is 1 liter. So this is the same thing as writing mole per liter. So let's give it a try. Here we're going to be dissolving 5 grams of nickel chloride hydrate in enough water to make 250 milliliters of solution. So I would recommend pausing the video, working this example out, and then starting the video again to see how it went. So let's see, we're trying to calculate the mole. So we're going to do this in 2 steps. We need to first calculate the moles of nickel chloride needed in our 5 grams. And once we know how many moles we have and we could figure out how many liters of solution we want, we could then calculate our molarity. So for 1, we know how many grams. We have 5 grams of nickel chloride. Using the molecular weight, we can change it into moles. And this molecular weight, this is 1 nickel, 2 chlorines, and then plus 6 waters. And that gets us this molecular weight. So now we know how many moles of nickel chloride we have in our 5 grams. Now we want our molarity. And molarity is moles per liter, so we can convert our milliliters into liters and end up with our molarity. So our final answer, here are square brackets showing that we have a concentration of 0.0842 molar. Here's the next example. Again, pause the video and try it on your own. So now we're looking for the mass of oxalic acid required to make 250 milliliters of 0.05 molar solution. So here we have our volume and our concentration. We're trying to find the mass. I do know our concentration is moles per liter, and we have liters. So we could figure out the moles, and once we have the moles, we could then figure out the mass. So using our concentration, which is 0.05 moles per liter, and I know how many liters I want, I can calculate the number of moles needed. Once I have the number of moles needed, I can use our molecular weight of oxalic acid to come up with how many grams are needed. And then my final answer is rounded to 3 sig figs. Here, going back to the problem, we have decimal present, starting counting from the Pacific side, 1, 2, 3 sig figs. Same thing over here, decimal present, counting from the Pacific side, skip, skip, 1, 2, 3 sig figs. So my final answer has 3 sig figs. So what we just did were 2 examples using solids, and you weighed out a certain amount of solid and then you dissolved it in water. A lot of the times though, when you're dealing with concentration, you might start with a very strong solution, and then you're going to dilute it until you have a much weaker solution. And when you're diluting your strong solution, all you're doing is adding water. So that means however much solute is in the solution in the beginning, that's how much solute you're going to have at the end. So the amount of solute stays the same. So here, for example, we can see it's a very strong solution, very concentrated on this side. We're going to dilute it, so we're just adding water. And now we can see we have a much larger volume, but it's now of a weaker concentration. But if you look at the solute on each of them, the solute stays the same because all we did was add water. So whenever you're dealing with dilution problems, basically what you want to do is you want to first figure out how much solute is wanted or needed in your final diluted solution. So they'll give you information for your final product. So the volume you want and the concentration you want. Using that, figure out how many moles you need. And once you know how many moles you need at the end, that's the same as the number of moles you need in the beginning. So once you know the number of moles you need, and you know how strong your initial concentration is, you can then calculate how much of it you need. So now we're dealing with the strong concentration. And then once you know how much of the highly concentrated solution you need, then you just add water and you end up with your diluted solution. Let's give it a try. So looking at this, here we're trying to prepare 2.5 liters of 0.665 molar Na2SO4 solution. So this part is our dilute solution, and our strong solution is the 5 molar solution. So let's see, what do we have? We have our information for the dilute and our information for our concentrated. If I know the molarity of our dilute solution and the volume of our dilute solution, I can calculate the moles of the dilute solution. Once I know how many moles of dilute solution, I know the moles are. Once I know the number of moles of our dilute solution, I know it's the same as the number of moles for our concentrated solution. Once I know that and my concentration, I can then solve for the volume. But I'm not done yet because it asks to describe how we would prepare this solution. So my final answer would then be to add water to our 0.333 liters of 5 molar solution. Continue to add water until you have 2.5 liters of solution. Another way to do that would be to say add 2.17 liters of water to 0.333 liters of 5 molar solution. And this 2.17 liters of water came from our total solution, 2.5, minus our 0.333 liters of concentrated solution that we've already added. You can't say, though, add 2.5 liters of water to our 0.333 liters of solution, because this initial solution takes up some volume in the beaker, and then our solution would be too large. You have seen this in equation form in honors chemistry. So if we are to look at our molarity equation, I know that this is moles per liter, or N per volume, moles per liter. And I know that in a dilution, the solute stays the same. The amount of solute is the same. So the moles stays the same. So if I rearrange this for the number of moles, I get N is equal to the molarity times the volume, or the concentration times the volume. And I know that the number of moles in the beginning is the same as the number of moles at the end. So in the beginning, I have a concentrated molarity and a small volume, and at the end, I have a second molarity and a second volume. So it's possible this formula should look a little familiar from honors chemistry. M1V1 equals M2V2. And the nice thing about this formula is that your volumes can be in any unit you want. Liters, milliliters, decimeters cubed. Doesn't matter, as long as they are both in the same unit, you're okay. So here are two practice problems. Give them a try, and then the answers are farther in the video. So looking at practice problem 1, how would you make a half a liter of 0.118 molar solution of solid silver nitrate? So basically we're going to have to measure out some amount of silver nitrate, add it to water until we have the correct amount of solution. So in the beginning, we know our molarity and we know our volume. Oh, that's not right. That should be, this is 500 milliliters, or 0.500 liters. And we're solving for N, number of moles. That does look correct though. So hopefully this is our number of moles. So this is how much silver nitrate we need, but we don't have any scales that can measure moles of silver nitrate, so we need it in grams. Using the molecular weight of silver nitrate, we see we need 10 grams of silver nitrate, but again, that's not done because we're asking how would you make. So you would measure out 10 grams of silver nitrate and add water until you have 500 milliliters of solution. Or you could also say add 500 milliliters of solution, or of water, sorry, not solution. For the second example, now we're diluting our strong 18 molar sulfuric acid until we have a weaker 6 molar solution, and we want 250 milliliters of it. So again, I'm going to start with our dilute information. We know the molarity and we know the volume, so we can solve for the number of moles. Once we have the number of moles, I know the number of moles are the same for the dilute and for the concentrated. So the number of moles are the same. So now looking at concentrated, I know the molarity, I know the number of moles, and I can now solve for the volume. Once I have the volume, I then want to know how would this solution be prepared. So I would measure out 83 milliliters of our 18 molar sulfuric acid, and then I would add water until 250 milliliters of solution is created. And here I changed my volume measurement to milliliters instead of liters. You could have kept it as liters, that's fine. However, I rounded it to 2 sig figs because everywhere in the problem is 2 sig figs. Another way to do the second example would be to use our M1 V1 equals M2 V2 equation, plugging in the information for our concentrated solution. We know the molarity, we're looking for the volume. Plugging in the information for our diluted solution, we can solve for the volume. And because our volume here was in milliliters, our answer for this volume will also be in milliliters. And again, then here's our final answer.